Okay, welcome to CS4510, L14A. The topic of today is recursion and truth. This is a bit of a retrospective on the unit that we've done so far. So what have we essentially shown? We have shown that there are like certain problems that are undecidable, or there are theorems that are true yet unprovable, and that it appears on the surface that diagonalization techniques are kind of like completely unavoidable, right? In the sense that self-reference does not appear that can be prevented by something analogous to a theory of types, right? So recall that Russell originally showed a statement of the form that it is false that X is an element of X, and he was able to use unrestricted comprehension to construct a contradiction. And Gödel used a little more complicated sentence that said something along the lines that while Russell used a paradox that said something like, I am not true, Gödel used a paradox that said something like, I am not provable. And the discussion about provability could never really be prevented, while Russell's theory of types did appear to prevent a discussion about truth. So, and sort of, he kind of like went around this, right? So then Gödel comes up and he says, you know, there are unprovable statements. And in fact, we also know that the halting problem implies Gödel's first incompleteness theorem, that the existence of an unsolvable problem. We did prove that the halting problem, if there is an unsolvable problem, then arithmetic logic cannot be both consistent and complete. So Gödel's first incompleteness. Right? But the halting problem is a bit complex, but in fact you can, just kind of as a throwaway exercise, you can in fact do a proof of unsolvability analogous to the halting problem, but much simpler and much more like Russell's paradox. In fact, rather than considering machine word pairs such that M does not halt on W, or M halts on W rather, consider machines that do not accept their own code. Okay, so what does this mean? Notice immediately the syntactic similarities between this language and this one, right? It's really this kind of the same thing. Here, M is a string to be accepted or rejected or looped upon by a machine, but also a language of machines to be a machine to run on strings. It's both a string to be executed on and a machine which runs on those strings, right? So there's a sort of a duality here between a syntactic representation of an object and a semantic one that is meaningful, the one that executes, right? So, and that's similarly here where you have an object to be contained and the same object which contains elements. These are the same symbol, but they kind of have different meanings. One is acted upon and one acts in, right? Same thing here. But we can prove this language is undecidable by a very similar proof to the halting problem. Assume to the contrary. Let's call it L. L is decidable with decider. Let's call it D. What should we do? Just open-ended question. Every diagonalization will kind of look the same, right? Every self-referential argument. So given that we have a decider for D, what question should we ask? I'll tell you. Let's take D, and what happens if we run D on its own code? Okay. Well, since D is a decider, it either accepts or rejects. So D on input D, suppose it accepts. That's true if and only if, by definition, the code of D is not an element of, is an element of L of D, right? But that implies, by definition of L, that the code of D is not an element of L, right? But since the LD is just L, that's true if and only if D on input D rejects. So D on its own code accepts if and only if it rejects. Contradiction, D does not exist. And such a language is not decidable, right? Very, very similar argument to the halting problem. Assume it is decidable, but this consists of machines that, this is a language of machines that do not accept their own encoding, right? So but the question is, is it decidable? Does that machine accept its own encoding? And if it doesn't, then it does. And if it does, then it doesn't. Kind of, that's their contradiction there. So D cannot exist. Such a language cannot be decidable. Now, the problem is, again, with the self-referential argument here. We appear to be able to take a machine and execute it on its own code, right? Suppose that Gödel's theorem, the halting problem, all these are actually theorems that stand independent of meaning. They are simply very formal statements about very formal systems. But we claim that these have some kind of correspondence with the intuition about what it means, notions of truth, provability, and computation. But those human intuitions are connected to these formal concepts of Principia Mathematica and so on by intuitive arguments. And perhaps if you make different intuitive arguments, you can construct a system that might be technically weaker, but not usefully so, but still analogously to being Turing complete, right? So suppose we wanted to limit this kind of behavior. The problem appears when you can take a machine and run it on its own code, okay? Let's suppose we create a programming language that prevents this. You can write all kinds of programs in this language, except you are not allowed to take, it is impossible to take a machine and run it on its own code. Could such a programming language be constructed? At a first glance, the answer appears to be no, right? Because let's suppose you did M on W, let's say this is like Python or something, right? It would just check if W is equal to the code of M, eject or stop or whatever, right? But in order to prevent that, let's say this was like by the compiler or something, hard-coded into every possible function. Certainly, it would need to know its own code in order to have something like this. So this does not appear to work on a first glance. And in fact, you can kind of get around this by having one program reference the second program, that second program referencing the first. That would also get around this problem. So this does not appear to work. Okay, fine. Here's a second idea. Prevent any input at all. So consider a programming language which takes no input. There is no transformations. We are simply talking about programs that take no input and run. It appears if it takes no input, you cannot run a machine on its own code, and therefore, that's it. You can avoid all kinds of self-reference. And that kind of follows from this. We know that Gödel's first theorem is followed from the halting problem, right? But it turns out that you can never prevent a machine from knowing its own code. This will follow from something we'll call Kleen's recursion theorem, and we'll talk about that later today. But Kleen's recursion theorem can be taken as a very simple corollary of a very simple fact. There is a machine which prints its own code. I'll say description. Does anyone know the name of these kinds of programs? The name of a program which takes no input and prints its own code. It's called a quine. Named after, not William, but Williard. I think that's right, quine. A quine is a program which takes no input and prints its own code. Okay? You can Google this. There's like code golf versions, like print the smallest quine, right? This is almost a trivial problem if you allow the program to read its own code off of disk, right? Let's say, read my uncompiled code, print that. It's going to print the string that is itself. But we don't want to allow this, right? So I claim, by the fact that there exists a quine, and a quine, again, is a machine that just prints its own code, takes no input, prints its own code, you can prove this Kleen's recursion theorem, and therefore you can prove the halting problem, and then from there you can get the undecidability, the incompleteness of first order of all logic, right? No kind of argument can ever be successful that prevents a diagonalization, because we can simply give the existence of such a machine. And that is true for any Turing-complete language, which kind of trivializes the whole thing. So by this chain of backwards implications, what I'm saying is, like, what is the core problem? Like, what is the first thing that ever went wrong? And could we have ever prevented it? And the answer is basically no. So you should be convinced that there is no, like, maximal subset of consistent arithmetic that we're actually working under, but rather everything is bad all the time, you know? No deviant version of instead of Turing machines, if we had machines with no input, we could still not avoid self-reference. A man who has no eyes and no ears still knows his own name. So let's give the construction, right? First off, we can't do immediate things, right? So here's the bad idea. Let's say we want this program to print its own code. So we're going to write the code as a variable here. We'll fill this in later. And then we'll say print m, where m is its own code, okay? Let's say we fill in the code here. We get, what is this, def main :n/t, m equals : def main, right? So the immediate problem is that this kind of technique would never work, because the code of m contains the code of m, right? So we immediately get an infinite kind of, an infinitely long program, which is not a program. So this would never work. That's not something that is feasible or achievable. So instead, we need to figure out a way for a program to exist to print its own code. Now, a program printing its own code appears difficult, but what we can get is two programs that print each other's code, right? So what we can do is have a problem called a helper, and instead of the main function having to print the main function, what we can do is have the main return the code of m to main, and then main will print that, right? But the code of this program is not just main. It is helper and main, right? So what we could do is have the code of main return to helper, the code of helper, we'll call it h, actually. And we can have the code of main be returned from helper with the code of main, right? So these two programs can return each other's code to each other. This is also going to induce such a similar problem. This is also not going to be able to complete. We're going to be circular, because the code of main is one that returns the code of helper to helper. So how does it know what the code is beforehand? We induce, in fact, the same problem. But we can modify this to get the intended solution, which is that instead of the code of main instead of main returning the code of helper to itself, what we do is we compute the code of h from m. Compute h from m. What we mean by this is we know what helper does. Helper takes on a string and gives that to main. But if you have this string m, you can in fact compute the program that does this, and then you have the code of helper. Then you simply print the concatenation of those two. This is all a quine is. And observe, there is no self-reference. Suddenly we have a program that prints its own code, but nothing here appears to say anything about the word I or me or anything like this. It's just programs that print each other, right? Analogously, this is, if I were to write this kind of program in English, it would be equivalent to the following. Print this twice, the second time, in quotes. And then the string to be printed would be print this twice. The second time. In quotes. So in English, if you could imagine like you pseudocode that up, that would be a program that prints itself, right? Print this twice, second time in quotes, and then the thing that it is instructed to print is not the full program, but a partial amount of the program. And the part where it computes the first program and the second program, or where it instructs it to print it twice, and it modifies the second printing, right? That's kind of what's going on here. This, again, is a program that prints itself, but there is no self-reference. There's nothing there that says anything like me or I or this is unsolvable. Nothing like that happens, right? Right, so let's construct the helper function and the main function. Helper is simply going to take no input. It's going to have hard-coded M. We'll figure that out later, and then it's going to return M. Okay? Then we call on the main function, and the main function, well, first off, we want the code of helper, and we want the code of main. So first we're going to say M is going to call helper. And again, helper and main take no input. Helper returns the code of M, we'll figure that out later, but it returns that to main. So main now has the code of M, okay? H should be what? The hard-coded code for the helper? Basically. Okay, there's a bit of syntactic sugar in the way there, program specific. Do we agree that H is a string, which is the code of helper? Okay, we're almost done. We're just going to print the concatenation of these two, call it H plus M, and know that it's different than M plus H, because M is a string, H is a string, so just print H plus M. We're not done though. We still have not finished writing the code of helper. We need the code of helper to contain the code of main. But now that we've done that, we're just going to take this and copy paste it there. Done. This is a program that prints its own code. All right. If you wanted to not distinguish between helper and main, you could even say something much simpler like this. Let M be the code, print, let M be the code that is something, but then we print M is equal to, and then the string M. And then we go back and we fill in M to be print, M is equal to M. Now, there's a small problem here syntactically, is that there's unescaped quotes, right? So there's a kind of a software issue, it's not a serious one, where these are, you'd have to backslash these, but then those backslashes would not appear here. Something like this, right? The way around this is that you just use a Gödel numbering or a hexadecimal encoding or anything like that, where you, instead of the string being as symbols that appear, it's just some hexadecimal number, and then you decode it here, right? That would solve this problem immediately. The problem of delimitation is not an important, in the theory of computation. It's like a very programming language specific thing, it doesn't really matter, right? If you wanted to be smart, I'm sure this would work. Those are usually reserved in Python for single syllable, but whatever, right? It's fine. Okay. QET, we've computed that there is a program that prints its own code. Quines exist. Questions on that? Okay. So we've proven there exists a program to print its own code. But it takes no input. Now suppose I ask you for a modification. There exists a program to print its own length. How would you do that? This is a classic, I think, counterexample where somebody, certainly if you have a program that prints every number, perhaps one of them must print its own length on accident. But I'm not convinced because the code of programs could always be, let's say, even. And it may be the case that it's skipped over or something. Because when you have the number 8 in there, it changes the length. It could be the case that the code of the program that says print 8 is always odd, but the code for some reason in the programming language, they're always even. Something like this, right? There's a smarter answer though.
You could compute the length?
Yeah, so just change this line. And then make sure you modify it when this gets included, right? So you would update it there as well. And then that would update it here. Okay? What else can you do? There exists a program to print its own code. There exists a program to print its own length. That's all Kling's recursion theorem is. Any program may obtain its own description and compute with it. I'll say it again. A man with no eyes and no mouth still knows his own name. It doesn't matter that previously we were able to perform diagonalization by passing the machine's code to itself, right? And if you prevent this at a surface level, at a syntactic barrier, then it doesn't really matter. Kling's recursion theorem says you cannot prevent this. It's still gonna work. The proof is incredibly simple. Repeat the argument, and then change, instead of printing its own code, you make the machine compute its own code. That's it. You just, for any computable function, you just modify this. Let's say we said main on input W. You say print F, which takes as input H plus M, and then W. That's it. That's the... Okay, any questions on Kling's recursion theorem? Are you convinced? Okay, so in fact, given Kling's recursion theorem, we can in fact prove that a quine exists much smaller. Here's how we could use Kling's recursion theorem. We would say M on input W, obtain via Kling's recursion theorem the code of M. And then we just say print the code of M. That's all it really is, right? Questions on that? Now, what is the significance of Kling's recursion theorem is it allows you to avoid this kind of discussion around like, oh, we're taking input, what if we don't want to take input? But in fact, we can prove the halting problem, Rice's theorem, and other things from Kling's recursion theorem much simpler. So again, let halt be the language. Right now we're proving that Kling's recursion theorem implies the halting problem. Let halt again be the language, M comma W, such that M halts on W, right? Assume to the contrary, halt has decider H. Consider the code of the machine D on input W. Okay? Will D halt on W or not? Well, let's ask our decider. If H says I am supposed to halt on W, no, I won't. And if it says, if the decider for halt says I will not halt on W, yes, I will. So I have my own code. Oh. First, I obtain my own code using Kleen's recursion theorem. What that means in practice is that I have set up this main helper kind of trick, okay? So I obtain my own code, and then I assume to the contrary that there exists a decider for halt. I ask the decider, oh decider, am I gonna halt on W? And if the decider says yes, I ensure that I don't. And if the decider says I won't, then I ensure that I will. So what does D on input W do? If it halts, that implies that H on D comma W rejected. But if the decider is correct, that implies that D on W looped. So D on W halts if it looped. And similarly, if D on input W loops, that implies that H on input D comma W accepted, which implies that D on input W halted. So we see that it halts if it loops. Contradiction halt is undecidable, okay? Much simpler argument than anything else, right? But notice that the core here was what? We ask it and we make sure we do the opposite, right? What else could be proven undecidable using the recursion theorem? Basically everything. Let P be this set of machines such that M has the property. Rice's theorem says if the property is semantic and non-trivial, then P is undecidable. Right? We can prove it with the recursion theorem as well. Suppose P has decider D. Since it is non-trivial, there are machines M0, M1 with M0 not in P and M1 in P. Because it's non-trivial, there's some machine that has the property and some machine that hasn't the property. They must exist, right? So we consider this machine M, which on input W obtains the code of M via the recursion theorem. And then it asks the decider about me. It says, if the decider says I have the property, then I won't simulate and if the decider says I won't have the property, yes, I will. Right? So the question is, does M actually have the property or not? So if M is not in P, then we know that the language of M is equal to the language of M1. But that would imply, since M1 is in P, so is M. And similarly, if the language, if M is not, if M does have the property, then the language of M is the language of M0, which doesn't have the property. So since M0 is not in P, then M is not in P. Done. Rice's theorem follows in a much more trivial fashion than it could ever from the reduction. Recall we proved Rice's theorem by reduction. We don't need to do reduction, we can do an immediate diagonalization in such a way. Questions on the power of the recursion theorem? I'll prove one more thing for you. Are you familiar with a fixed point theorem? Are you familiar with the term fixed point theorem in any context?
I know the fixed point combinator.
The Y combinator?
Something like that.
Yes, the Y combinator is essentially analogous to a universal Turing machine. It's like it takes as input the description of another lambda, and it does what that does, essentially.
Yeah.
I suppose, let me give you an example of a fixed point theorem. The classic one is due to Brouwer, who was also the intuitionist. And it's like if F is continuous from, let's say, two closed sets, then there must exist some x naught such that f of x naught is equal to x naught. Some function with some, if the function is continuous and it is from closed set to closed set, then there is some point that is not mapped. It does not change after the map. Like everything else may shift around except that one point. That's not true in a discrete sense because of like permutations. Obviously you can just shift everything over by one. But for any continuous function with such a property, this must be true. So a fixed point is something that after performing the function, it does not change. We also have a fixed point in computability theory. Let t be a function from naturals to naturals be any transformation of Turing machines. What we mean by a transformation of Turing machines is that we map M0, M1, M2 to MT of 0, MT of 1, MT of 2, and so on, right? What a programming language is, by the way, in the most formal definition, is which strings map to which recognizable languages. So the order of, an ordering of the recognizable languages is defined to be a programming language. That's the formal definition. So you should think of T here not as one that permutes the indices necessarily. Let M0, M1, M2 be a canonical ordering of the Turing machines based lexicographically, for example, shortest strings to longer strings. And let the reordering be T0, T1, T2, right? But this is true for any possible function, where you think of it as a transformation. For example, T could be the function that swaps the states, the accept and reject states. T could be a function that relabels the states. T could be a function which maps all Turing machines to one Turing machine, and so on. But we represent it as a function from naturals to naturals in this way, right? This is just any transformation. So you take a set of objects, a set of Turing machines, and transform all of them. Another way to write the recursion theorem as a fixed point theorem is that for any transformation T, there must exist I such that L of M of I is equal to L of M of T of I. No matter what the transformation is, for any transformation you can think of, every transformation has a fixed point. Perhaps a different fixed point, but every transformation has a fixed point. For example, let's suppose I ask you for the transformation that swaps the accept and reject strings, okay? Give me the fixed point. What Turing machine, if you swap the accept and reject states, does not have its language changed? Oh, there's one requirement here. The transformation must be computable. Most of the transformations, of course, will be computable, but let's require it. I ask for a transformation of Turing machines to Turing machines that swaps the accept and reject state. after you swap the accept and reject states of all Turing machines, which machine does not have its behavior changed? I'll give you a hint. It's a machine that would never even touch the accept. It's just one of the fixed points would be a machine that never even touches its accept and reject states. So it would be, for example, the machine that loops on all inputs. A machine that loops on all inputs recognizes the empty set as its language. So if you swap the accept and reject, it still recognizes the empty set, right? So that, in fact, does not change its language. And for any such transformation, I promise you can always find such a thing, right? Proof, let's prove it. Consider this machine M on W. We're going to first obtain the code of M via Kling's recursion theorem. We're going to compute I such that the code of M is the code of MI. What are we doing? We're asking for our index. If the programs are sorted lexicographically, which machine am I? How would you do this, right? This is a programming question. How would you determine your index? How would you know, for example, if you have access to your own code that you are like the third machine? I could also just tell you, just brute force search. Try all strings lexicographically. If they pass the compiler, if they pass the syntax checker, I++, do so until you find your own string, and that'll tell you the index, okay? Then, because t is computable, we can just compute t of I. Find or compute m of t of I. How could we find m of t of I? We have I, we have t of I. Rather, I should say we find this string. The answer is just brute force search again. If we have a number, we know what the ith program is. We know the t of ith program as well. Just like search through all strings, counter plus plus until we hit the 287th program. That's lexicographic, right? Now that we have m of t of I, we're just going to say simulate m of t of I. Done. M here is the ith machine, and it'll do whatever. It computes what its transformed index was supposed to be. It computes its own transformation in some sense, and then simulates that. So it says, oh, you're going to swap accept and reject states? I know my own code. I'm going to compute my own transformation and then simulate my transformation. That is the fixed point for every such transformation. It computes itself. It computes the transformation itself and simulates that. Done. We have a fixed point theorem now for, in computability theory, analogous to one that exists in calculus. Right? There are thousands of fixed point theorems in geometry, in topology, and analysis. They're everywhere. And they even appear here. Right? No matter what reordering of the recognizable languages you choose, there exists one that never changes for any possible reordering. Done. Questions on Kling's recursion theorem? Okay, we've talked about recursion in significant depth. Let's now talk about truth. So truth, what is truth? Truth is it's hard to say, and that's kind of the point of the second half of today. It's very feeble, and it's very delicate, right? So what does it mean for a sentence to be true? Like, if I asked you this, what would you say it means for a sentence to be true? This is an open-ended question. When is a sentence true?
I guess when you have factual evidence to back it up.
In an evidence-based, and there's kinds of theories of science that say it is the case that it is consistent with the facts. That's probably the best definition of truth one could ever give. But let's suppose we're working in a purely logical system. We're only dealing with, just to simplify things, not to make your answer wrong, but just like, let's suppose we're working in an ideal logical system. When is a theorem true?
Never been proven false.
That is true. But recall we have Gödel's first incompleteness theorem that some statement is true but unprovable.
But they're still true though.
It is still true, but there is no demonstration of its falsehood. So if you cannot demonstrate it to be true, yes. If you cannot demonstrate it to be false, it must be true. I would accept that, mostly. In the most general, I'll give you Aristotle's definition. And it's a bad definition. To say of what is that it is not, or of what is not that it is false. While to say of what is that it is, or of what, of what not that it is not is true. Okay. That's Aristotle's definition of what it means for something to be true, what it means for something to be false. Classic Greek fashion, it's nonsensical. Remember that the definition given by Euclid of a point is that which has no part. But in some sense, you cannot ask for really anything more, because what is a point if not the intersection of two lines? But then the definition of a line is a sequence of points. So you end up with a similar problem. This references that references this, right? So this is honestly about as good as you could ask for with respect to any kind of logical, this is about, honestly, as good as we're going to get. And Tarski was this logician. He wrote extensively both for philosophers and logicians about what it meant for something to be true. And upon inspection of something like this, the best definition we can give in a purely formal sense is truth is a very strongly semantic property. But we are asking about the truthfulness of sentences. So for example, let's say I ask you the sentence, snow is white, is true if and only if what? Forget the snow is white part, right? But snow is white is a true sentence when what is true? All truths are in equal truthfulness, but we can give it, that's a great point. All truths are the same truth. At least in a formal sense, maybe not in a scientific sense. In the spirit of not giving a real answer, snow is white is a true sentence when snow is white. Okay? So the definition, the Tarskian definition of truth, is that some encoded formula is true if and only if that formula is true, right? The difference here, again, is the connection between syntax and semantics. We are asking a question about a syntactic object, a sequence of symbols and strings. Snow is white is a sentence, but we state that the sentence is true if and only if the semantic meaning of that sentence is true, right? The notion of truth must be fully explored because of this whole issue that Gödel and Russell raised, right? Truth, as we know, is relative to some set of axioms. And a statement is said to be true in a primitive sense, two things. One, if it's not false, and two, if there's a proof of it, right? Anything that is provable must be true. We have this property called soundness. But we know Gödel showed that there are things that are true but not provably so. So the notion of being true is a very strongly semantic property, right? And in fact, it is not necessary, it's very difficult to base this semantic property on the sentence itself. And there's a classic example of this given by Kripke. Consider the following two sentences. Most of Nixon's assertions about Watergate are false. 2, everything Jones says about Watergate is true. Okay? These are just two sentences. There is no self-reference. Neither person is saying anything about each other, okay? But suppose it is the case that Jones says 1. Okay? If Jones says 1, and we know that, so if 2 is true, then everything Jones says about Watergate is true. Jones says 1, therefore 1 must be true. 1 is most of Nixon's assertions about Watergate are false, right? In the sense of a majority. So, what if it's the case that Nixon says 2? Then again, we see that 1 is true if and only if it is false. And similarly for 2. But there is no self-reference, and in fact, note that there is no reference. The reference occurs not at any part of these sentences. These are sentences, and we seek to evaluate their truth. But the truth of the sentences is not dependent upon their structure in any syntactic sense. It is dependent upon the facts of the world. These properties, where Jones says 1 and Nixon says 2, are not properties syntactically of the sentences, but are properties of the reality of the world, right? These are what makes this self-reference exist, but it's nothing to do with the sentences themselves, right? That's the first thing to note. The truth, and this is why you can never really prevent any kind of diagonalization argument. So we're making two arguments. The first one was in a computing sense, the recursion theorem is true. You can never prevent self-reference. Here we're explaining in a logical sense, you could never also prevent self-reference, right? So when you take basic, the first moral of something like this is like, you could never fully formalize linguistic language into a formal language simply because, in a way that is not self-referential, because reality contains such things that can never be prevented, right? Nothing is inherently self-referential about those, and the problem occurs not by the sentence structure, but by the facts of the world. That's the moral of that, right? So again, we have some problems, and we seek a better definition of truth. So Tarski gave this definition of truth, which is that a statement is true if the meaning of the statement is true. But such a statement is not very good, right? We could ask is like, what could possibly be a better definition of truth? And recall that we have something like the recognizable languages and the decidable languages, right? These are the way things are. Things are recognizable, they're co-recognizable, or they're decidable. Things kind of fall into these cases. And the set of provable statements is recognizable, decidable, or co-recognizable. It's recognizable. Why? If a statement is provable, how would you demonstrate it?
Just simply have proofs for it.
Yeah. So a more formal answer would be just search for the proof. If it exists, you'll find it, and that proves it. So if such a statement is provable, you can at least always recognize it to be so. Okay? So provability is at least, the notion of provability is at least recognizable, right? What about the following language? This is what we're going to say is Tarski's theorem is that this is some larger class of objects that are not computable, decidable, recognizable, whatever, but simply definable in a formal language. This goes out here. Here's what Tarski says. Truth of arithmetic cannot be defined in arithmetic. You cannot, although you can give a formal definition of when a statement is provable, you can never give a formal definition of when a statement is true. It's impossible. We have, in some sense, the strongest undecidability result, which is that not only can this thing not be half decided, or it cannot even be defined, right? Now, when I say this English sentence here, phi is true, this could never be written in a formal language. You can always write provability in a formal language. For example, we may say that a formula is provable when there exists a proof of it, right? So we may say there exists some p such that p demonstrates x. And this demonstrates relation is a very complex 46 formulas of ands and ors, quantifiers, inductions, whatever. Gödel described how to give such a formula, right? We may create a predicate that takes as input numberings of formula or just the formula, and it is true or false depending upon if a formula is provable. Now this can always be constructed, okay? So provability of arithmetic can be defined in arithmetic because you can always construct a formula. So this is what it means to be definable. It's defined formally. True cannot. You can't do it. There's no formula for it, basically, is what we're saying. There's not a formula for truth. Let's prove it. Before we do the proof, what would you guess the main technique of the proof is going to be? Yeah.
I don't even know if we can prove the truth of something because of Gödel's calculus. Is it?
You can never prove, that's a good point. You can never prove that there exists true but unprovable statements. So there are things that cannot be proven. But what I claim here is that we can prove there is no formula, no definable way to represent a truth predicate in arithmetic. You can always define you can define provability. You cannot define truth. So the definition of truth cannot escape anything that is above Tarski's definition, in some sense. Too simple to be useful kind of thing, right? One more time I could ask is, what technique do you expect us to use in the main theorem?
Maybe diagonalization?
It's going to be diagonalization. Every proof is diagonalization. You could, in fact, just prove this language to be undecidable by a simple argument. But we seek something stronger, that there is no truth predicate for it, right? And in fact, if there was a truth predicate, then this would automatically become decidable because then this predicate could just go there, right? Assume to the contrary, that the predicate true is definable. Recall how we did Gödel's first incompleteness theorem, right? We took a formula of the form f of x was there does not exist p such that p demonstrates if you take the substitution of x, 17, and x, right? And then you plug in some steps, and then you got that through this sub x, 17x, we got f of gamma of f was equal to does not exist p such that p demonstrates f of gamma of f And then we said let this be called G, so we said that G asserts that there does not exist P, such that P demonstrates G, right? So in some sense, G is not provable. Why don't I just make these if and only ifs instead of equalities, okay? Notice, though, what really did not change as we performed this kind of self-referential diagonalization. The word dem here, the exists P here, this whole part did not change. But using this substitute x17x part allowed us to reference a formula on the outside and the inside, right? So if such a predicate was true, then we could construct something like f of x to be that it is false of true of substitute x17x, right? If such a predicate was definable, we continue with some steps. We would rename our thing to get t, and we would get t if and only if it is false that t is true. We could repeat the same diagonalization argument we did in Gödel's incompleteness theorem, but instead of having this exists P demonstrates the thing, as in that says that P is provable, here we replace that definition of provability with a definition of truth that we assume to the contrary must exist. Okay? Now, what do we know about the truth of T? We know that by Tarski's prior definition of truth, we know that T is true if and only if snow is white is true if and only if snow is white, right? So we know that true of T is true if and only if T, right? But here we know that that means that the predicate T returns false, is false, if and only if it is supposed to be true. So truth is undefinable. Done. Now that's kind of problematic, and so what is the resolution of this? I mean, like, so we talked, there is a resolution in the context of like Gödel and Russell had earthquake level issues where people kind of knew what direction to go and which ideologies would die off, which new ones would spur up, things like this happen. So if truth is undefinable at a philosophical level, what would you conjecture that really means? Basically, people kind of fractured and started saying all kinds of crazy things about what it means for truth to exist. Some people went even deeper into this route that undefinability, undefinability is a far more stronger notion than undecidability, because at least the halting problem can be defined. Provability at least can be defined. Truth is such a stronger and prior notion, it cannot never be defined. And so people immediately turn to the problem of like, we can't really formal language, like intuitive language, human language, again through Kripke's example, could never ever be made formal, right? But we still we need a definition of truth. We can't do math if we don't have a basic notion of truth. Forget reference, we need the notion of truth. So the closest thing that we have is a coping mechanism, which is this, I don't know what you would call it, like a meta-language hierarchy. There exists a language L, which is the object language, right? And objects are discussed in this language. But then the language is defined by a meta-language. And a meta-language is the rules of the object language. So and then of course there's a meta-language, right, that defines the language of things that are in the meta-language, right? So there's mathematics, and then there is mathematics about mathematics, which is meta-mathematics. And then there's rules that govern what is allowed in meta-mathematics, which would be meta-mathematics, right? And so on. You could go all the way back up. But what we could say then is there is no perhaps universal predicate of truth where you'd merge all these problems. And you ought to, but you could perform kind of like a terrible version of gerrymandering that in the sense that you prevent discussion of, it's analogous to the theory of types in which objects can only reference those below it. But instead of saying something Russell-like, where you would say this sentence is false, which would be not in any specific language, you could say this is false in O. And that would be by saying something like that, you would say this is false in the object language. That statement itself is an assertion about something in the object language, so it would actually be in the meta language, right? The meta language would have its own truth predicate, the object language would have its own truth predicate, and the meta language would have its own truth predicate, and so on, right? In the pure propositional logic, there are actually definitions of truth, right? When is P implies Q, when is P or Q true?
When just one of them or both of them are true?
Yeah,
Yeah.
so the predicate you could define in pure propositional logic would be that P or Q is true, a truth function would be defined to be right? In the English sense, right? So you can recursively, the truth of a proposition is dependent upon its subpropositions and so on. And that's not too difficult to prove in pure propositional logic. But you start throwing quantifiers in there, you start doing advanced things, things get out of hand pretty wildly, right? So one coping mechanism we have is the distinguishing between the object language, the meta meta language, and so on. And therefore, each one may have its own truth predicate, and there is no universal truth predicate, but as a coping mechanism, we still can discuss truth in a very limited relative sense, right? This is not going to fully work, though, because there is no universal notion of truth. I would hope truth to be universal. It's such an identity, it's such a core concept, you could never escape it. But, yeah, best we can do. Questions? Tarski's undefinability of truth, the recursion theorem? Okay.